Howdy, we are Safe Haven Technologies, and we are presenting our project Hostile Weapon Detector with Advanced Sensors and AI. Introduction. My name is Corbin Fraser, and I'm the project manager and level 1 software engineer.
I'm Eric Rahman, the software engineer.
I'm Juan Rojas. I'm the mechanical and hardware engineer.
Background. Our problem statement. The current status of security detail equipment, and this is specifically for metal detectors, currently goes for $4,000 to $5,000 per unit. This also includes metal detectors being notoriously inaccurate for having false positives and false negatives frequently, which forces security detail personnel to constantly monitor the metal detectors and to take measures that go beyond that, which costs money for salaries. With federal entities, specifically schools that we are interested in targeting our prototype for, their budgets are extremely limited, and if they can, it would be very hard for them to afford multiple units of $45,000 for each entrance, plus security detail to monitor and maintain these units.
An existing solution on the market is Zero Eyes, which is a company focused on selling AI-based weapon detection software. A disadvantage of this solution is they are unable to detect concealed weapons, and their business model is selling contracts to customers to use Zero Eyes software or cameras. Below are some examples of their camera and contract pricing. Another solution is the Evolve Express system from Evolve Technology. Evolve Technology is focused on developing concealed weapon detection with AI. They sell a service to customers to use their technology and metal detectors rather than selling a product. It costs about $2,500 to $3,000 per month in a 4-year contract. So for $2,500 per month over 48 months comes around to $128,000, and upfront cost for standard metal detectors is $50,000. Evolve Technology is currently going under a lawsuit in 2022 because a knife was passed through and wasn't flagged. Existing solutions are selling contracts to customers instead of a product, and this strategy restricts accessibility. Our solutions replace multiple units of walkthrough metal detectors and wands for a single advanced detector, and we are integrating AI to automatically detect concealed weapons. We aim to make our solution compact and modular. The impact of the solution results in delivering affordable and budget-friendly concealed weapon detectors that grants more federal entities accessibility to concealed weapon detection.
Our goal for our project is to reduce redundancies. Our project is inherited from a previous semester, and so our goal is to reduce the redundancies that they previously had and to make our system more efficient. We are integrating computer vision for human detection and human tracking. We are going to implement an optimized. We're going to implement path optimization to decrease operational time, and we are going to add a machine learning model at the end of the pipeline to automatically detect the heat map of metal weapons with our millimeter wave radar. This is our conceptual block diagram. This is a wide overview, and we're going to take it number by number. Starting with number 1, the camera will first take a picture of the subject of interest, and that photo will be sent to the Raspberry Pi 5. The Raspberry Pi 5 will then draw a boundary around the subject of interest, and our path generation algorithm will create a path for the radar to travel. Going on to number 4, the path that is generated, the Raspberry Pi will then execute on the gantry, and the radar will follow that path. The radar is the red box. It will scan the subject of interest, and if we go to number 5, the raw data will go to the computer, and the computer will process this raw data and generate a heat map where the metal weapon will burn bright red. Performance specifications. Customer requirements. This is a inherited gantry, and we have to use the gantry and sensors, the IWR 1443 and the DCA 1000. We are going to continue the development of this gantry in the system. We're going to integrate computer vision for human tracking so that we can track our subjects of interest. We're going to optimize the gantry path and gantry operations so that we can reduce operational time. We're going to increase the gantry speed to further reduce time. And then at the very end, we are going to add an AI weapon detection system.
The electronics used is the DCA 1000 evaluation module. It is a processing board and is responsible for transmitting data through Ethernet. The IWR Boost 1443 millimeter wave board is responsible for transmitting and receiving millimeter wave. The camera used in our system is the RUCam Pi Camera Module 3 Wide. We integrated YOLO V8 model for human detection to identify starting position for scanning. And the microcontroller controlling the motors is the Raspberry Pi 5.
In terms of mechanical and hardware, here's a front view of how the gantry model looks in SolidWorks. It is 35 inches by 36 inches XY gantry system. The outer dimensions are 35 inches by 41 inches, with the extra height being provided by the slots holding the vertical ball screw. The inner dimensions are 29 inches by 24.63 inches. The system is using 2 SFU1610 ball screws and 2 1000 RPM step motors. Here's an isometric view of the system. The system consists of what I like to call 7 subsystems. The gantry system itself is the entire system with 7 subsystems. These consist of the base, the horizontal ball screw, the vertical ball screw, the linear guide, the vertical motor base carriage, the rail guide, which is meant to prevent the vertical ball screw from freely spinning due to gravity, and the button mount. All these subsystems together create the gantry system. Some of the big changes in the system are replacing the previous Arduino Uno with the Raspberry Pi 5. The old system used to run on 2 computers and the Arduino. The way this worked is the 2 computers we used to gather data with the Arduino, sole purpose to control the motors. The Raspberry Pi 5, in our case, acts as 2-in-1. It is a computer, so it has better access compared to something like an Arduino. Here's a before and after. The image on the left is the system we were given, with the system on the right being the current system we are using. Some of the big changes in the system are replacing the previous Arduino Uno with the Raspberry Pi 5. The old system used two computers and one microcontroller setup. They were using one computer to purely control the Arduino Uno and by extension the gantry motors. The Raspberry Pi 5 acts as two-in-one, in which it combines a computer and microcontroller to preserve the function of controlling the motors while eliminating redundancy in the setup. In addition, a camera was added to take a picture of the subject of interest. This then creates a boundary for which the gantry system will follow and scan. This is used to help reduce scanning unnecessary areas that give us little to no information. For example, a person would typically be in the center, so to avoid wasting time, we just have it scan that particular area, not scanning the very right edge or the very left edge. Of course, the biggest change was changing the old bell-driven system to a ball screw system for more precision and accuracy. While the bell-driven system is faster, it had a bunch of issues when it came to vibrations and stability. This ball screw system fixed those issues by offering more precision to be more steady. In addition, an emergency stop button was added on the bottom right to immediately stop the system should an emergency occur. This was mainly added as a safety feature since there wasn't one on the previous system. So now, should any emergency occur, that button is there and can be used to stop the system without having to directly go and unplug the whole power supply that's powering the system. The frame has also been improved to further stabilize the system and reduce the effects of vibrations. So the old system was kind of, you could wobble the system, the legs, for example, and the entire system would move. With our current system, that is no longer the case. Another safety feature we've added are reed sensors to prevent the gantry system from falling off. For example, the system can slide off if it went all the way to the right, but these sensors will halt the system when the sensors interact. Track chains were added to assist with cable management and avoid having wires get caught when the system is operating. Many of our electronics are located in the back of the gantry, including our Raspberry Pi 5 and our powered PCB board.
So for software role in the system, so firstly, there is a Lua script that will execute inside a millimeter wave studio that performs the radar capture. It sends a configuration to the board, to both of the boards, to configure them in the way that we want. And this is also variable. You can change the settings in the script to do research level scanning. Now, the Lua script coordinates the gantry motion by sending commands to the Raspberry Pi over SSH through a local command prompt or PowerShell. By doing this, it can capture and scan deterministically, as the scan will wait until the actual motor is moving, or vice versa. The scan will trigger and the motor will trigger concurrently, and this ensures that scanning is synchronized with the motorized movement. Now, we can also monitor the movement and ensure safety while it is processing by coordinating it with the reed sensors to recalibrate the system to its true origin, its physical origin. And then we also have the emergency stop button to ensure safety. That will be a software control on the stopping of the motors. However, it will continue automatically. In this point in time, the radar capture is still automated and will continue to send the gantry motion. After stopping, it will wait a while until the next pass is supposed to happen, and then it'll keep moving again. So after using the stop button, it's critical to also disable power to the motor if possible. Now, after we ensure a safe scan, we use a Python file for synthetic aperture radar reconstruction, and this will use fast Fourier transform for simple reconstruction. This will happen quickly, and it can happen at different z steps from a set determined range. Now, we will convert this millimeter wave bin files, 40 steps in our case, 40 Y slices, to a 2D and 3D heat map. That'll be a 2D map with a step through in different Z steps. Now, the end-to-end flow is as I described. The last step in the ML pipeline, or the last step in our pipeline, is the ML itself. So we are aiming to replicate the paper of a research paper, if I can remember the name of it. It's integrated modeling and target classification based on millimeter wave SAR, and this research paper proposes. Okay, so the ML training is going to be based on this paper called Integrated Modeling and Target Classification based on millimeter wave SAR and CNN approach. So what they do is they just grab online images, they add artificial reflectivity map onto it, and then they'll use that as actual training data to feed into CNN. And basically, from my understanding, it's going to look as the online resource acts as a base for a simulated scan and what it would probably look like. And then we use that as basically our training set so that we can quickly get a lot of images, a lot of scans, and feed that as training data. Not the actual optical images themselves, but the reflectivity added images. So that's our proposal for the training for, or the last step in our pipeline is the ML itself. So we are aiming to replicate the paper of a research paper, if I can remember the name of it. It's integrated modeling and target classification based on millimeter wave. Okay, so the ML training is going to be based on this paper called Integrated Modeling and Target Classification based on millimeter wave SAR and CNN approach. So what they do is they just grab online images, they add artificial reflectivity map onto it, and then they'll use that as actual training data to feed into CNN. And basically, from my understanding, it's going to look as the online resource acts as a base for a simulated scan and what it would probably look like. And then we use that as basically our training set so that we can quickly get a lot of images, a lot of scans, and feed that as training data. Not the actual optical images themselves, but the reflectivity added images. So that's our proposal for the training for weapon classification.
If a unit was to be recreated, we assume that labor wage for assembly is $9 per hour, assembly time is 20 hours, which comes to a total cost for assembly $180 per unit. Complete cost, including material and assembly, is $3,693.09. Our actual project expenses, we had a budget of $1,000 and it got approved for a $500 extension. And the cost of our system, not including shipping and tax, is $1,993.47. And we went over budget by $493.47.
These are our sources. Thank you so much. This is Safe Haven Technologies. I hope you enjoyed our project.